This video will discuss the vibrational partition function for molecules in statistical mechanics. So we want to get the partition function for vibrations of molecules, which will be a sum over all the energy levels of their degeneracy times e to the minus beta ei, the Boltzmann factor, where beta equals 1 over the Boltzmann constant times the temperature. So what we use here is the model for vibrating diatomic molecules is the harmonic oscillator model. We have two atoms of masses m1 and m2. They have some bond distance r from one another and some equilibrium bond distance r naught. They're connected by a spring, which is a spring potential and spring constant of k. The reduced mass of the system is the product of the masses m1 times m2 over m1 plus m2. The vibrational frequency of this diatomic molecule is 1 over 2 pi, square root of the spring constant divided by the reduced mass. And nu bar is 1 over 2 pi times the speed of light times square root of k over mu, or nu bar equals nu over c, where in wave numbers, the typical values that you'll see for vibrational constants is around 100 to 5,000 wave numbers. So note that the rotational constants, which are typical, are about 1 to 10 wave numbers, whereas the typical vibrational constants are around 100 to 5,000 wave numbers. All right, so the energy levels that come out of quantum mechanics, which you can look at in the harmonic oscillator playlist if you prefer, depend on a quantum number n, and they're equal to Planck's constant times our vibrational frequency times the quantum number n plus 1/2. So n is a quantum number that starts at 0 and it goes up to infinity, and the degeneracy of each energy level is going to be 1. So our vibrational partition function is going to be a sum from n equals 0 to infinity of e to the minus h nu over kt times n plus 1/2, putting in our Boltzmann factor up there. We can also define a new quantity called the vibrational temperature, just as we did for the rotational temperature in the previous video. Theta vib equals h nu over k, also equals hc nu bar over kb. So c is the speed of light here in centimeters per second, h Planck's constant, and kb Boltzmann constant. The Boltzmann constant in wave numbers again is 0.695 wave numbers per Kelvin. So theta vib is just about 1.4 times nu bar. So typical values for vibrational temperature you'll see are on the order of kind of 200 to 7,000 Kelvin. All right, so substituting that in, our vibrational partition function is equal to the sum from n equals 1 to infinity of e to the minus theta vib over t times n plus 1/2. So we can factor this out. This 1/2 here is going to be minus theta vib over 2t. So that's a factor that's going to be in every single term here, and it's constant. So we can factor that out because e to the a times e to the b is e to the a plus b. So we're factoring it out. We get e to the minus theta vib over 2t times the sum from n equals 0 to infinity of e to the minus theta vib over t to the n. So e to the kx is equal to e to the x to the k. So I've factored out this to the n here. Now this is a rare case where this is a sum that we can actually carry out. So the sum from 0 to infinity of x to the n is equal to 1 over 1 minus x if x is less than 1. So e to the minus theta vib over t, so theta vib is a positive number, t is a positive number. So typically what we're going to see here is this is going to be some e to the minus positive number, which is 1 over e to a positive number, which is going to be less than 1 for all values of t and all values of theta vib. So this is actually equal to, so the sum from n equals 0 to infinity of e to the minus theta v over t to the n is equal to 1 over 1 minus e to the minus theta v over t. So we take that sum and then we multiply it times the part that we factored out here, And what we have is that our vibrational partition function for a diatomic molecule is equal to e to the minus rotational temperature over 2 times temperature over 1 minus e to the minus vibrational temperature divided by T. Now, under the harmonic oscillator approximation for a given diatomic molecule, this is actually exact. So it's not going to be exact for real atoms and molecules because they're not perfectly harmonic, they're not perfectly harmonic springs, but under the harmonic oscillator approximation, this is the exact partition function. We didn't make any approximations to carry out this sum as we did for the rotational and translational partition functions. So for a diatomic molecule, this is actually an extremely accurate partition function. And so what do we need to do to generalize this to polyatomic molecules? So for diatomic molecules, they only have one rotation. The number of rotations for a linear molecule is, they only have one vibration. The number of vibrations for a linear molecule is 3n minus 5. Diatomic, n equals 2, 3n minus 5 equals 1. For a general linear molecule, they have 3n minus 5 vibrations. For a nonlinear molecule, they have 3n minus 6 vibrations. So they'll have that many vibrational constants and that many vibrational temperatures. So the total vibrational partition function is going to be a product of all of the individual vibrational partition functions. So it's a product of from I equals 1 over all of the vibrations of the individual partition functions of each vibration. E to the minus theta vib I over 2t over 1 minus e to the minus theta vib I over t. So this is true for a general polyatomic molecule. Generally, you'll be able to look up in some table what are the vibrational constants for that given molecule, convert those to vibrational temperatures. If they give you vibrational temperatures in a table, even better, just substitute those directly in. Compute this quantity for each vibrational mode, multiply them all together, and that will be your vibrational partition function for this given molecule. So as I said, for translations, there are an enormous number of states which are occupied at 300 Kelvin for most molecules. For rotations, they're typically on the order of 10, 20, or 30 vibrational or rotational levels that are occupied. But these energy separations are getting quite large, and so for vibrations in the ground state, vibrations at 300 Kelvin, most molecules are in the ground state. So your vibrational partition function, if you're in the ground state, exclusively would just be 1. So usually it's some number which is slightly bigger than 1, like say 1.03, 1.01, 1.001. Usually some number which is slightly larger than 1, because most molecules are in the ground vibrational state at room temperature.